We're going to be looking at regional compilation of local data sets. So that's a regional compilation of landform ages. In this case, each age that is plotted on a graph represents the age of a landform, and that age represents several individual TCN ages that form some sort of viable cluster. So at least 3 individual TCN ages for that landform. And we're pulling this data from the compilation in Himalaya done by Oren and Dortch in 2014. And I've separated this data into 5 age ranges that are based off of natural breaks, but really kind of generally order of magnitude changes within the data set. Again, these ages have not been recently recalibrated, and the analysis here is only meant as a tutorial on how to run PCAT to look at regional compilation of ages. And we're not trying to supersede the previously published results. I don't even think all the ages are in here actually, just the vast majority of them. So the real distribution would be a little bit different. So when we're thinking about ages of individual landforms, we're trying to find the best cluster, right? And through this program, for older landforms, we recommend taking the oldest component Gaussian that has 3 or more ages, and for younger landforms, we look at the highest probability component Gaussian that has more than 3 ages. This is a little bit different because it's a regional compilation. Each age that's plotted on here is already a viable independent age of a landform. And what we're really trying to do is deconvolve or break down the probability density estimate into as many small pieces as possible. This will allow us to distinguish individual kind of events where things align. In this case, these are all glacial features, glacial moraines, and I think the vast majority of it is beryllium 10 data. So we're really looking at timing of deglaciation events. So as you would have seen in the local landform age analysis video, the MAD bandwidth is probably going to give us the narrowest result and break apart clusters into smaller pieces compared to the other bandwidth estimators when we have lots of samples. And with a regional compilation, you're of course going to have a lot of samples. Another really important difference, this is regional data. We want to build our probability density estimate based off of external uncertainties. Another difference is that with very old landforms, which you see clearly here, I have labeled very old landforms, we want to look at the natural log of the data when building that distribution and plotting. We will look at linear ages as well, just for comparison's sake, but we're going to get much better results by looking at the natural log of the data because it deals with the very old ages, 300,000-400,000 years old. It deals with the probabilities a lot better, it makes them a lot tighter. So with our external uncertainty set and we're in natural log mode, we can start running our 3 different bandwidths. Okay, and so we ran the mean bandwidth estimator and we have a nice fit here on our model fit with the 1-to-1 plot. So we'll set that aside and let's run the standard deviation interquartile range bandwidth estimator. Another good fit, a lot faster. And let's run our MAD bandwidth estimator. Another difference that you'll see when we use external uncertainties is that for the 1 sigma uncertainties for the component Gaussians, you'll see not available. That's because we're running with external uncertainties, so only external uncertainties are available. Here we have a little bit of dispersion, but it's symmetrically distributed across this 1-to-1 line, and it's not very far off that 1-to-1 line axis, so I think this is totally acceptable. The mean and the standard deviation are effectively statistically indistinguishable. 108,000, 152,000, 358,000, basically the same. This one's off by, maybe 1,000 years. 3 distributions seems fairly reasonable. The MAD bandwidth estimator gives us 5 component Gaussians instead of 3. We're catching these 2 out here in this Gaussian 5, these 2 in Gaussian 4. We have a cluster here for Gaussian 3, and we're kind of splitting up this lower cluster between these kind of 3 ages and these other ones in Gaussians 1 and 2. I'm sure that the shared probabilities probably go a little bit further than that. but I think that this is probably going to be a better way to go, especially dealing with this older data sets and breaking these apart in a more realistic way. While the uncertainties are large, these are very old ages that are pretty far apart from each other. This is 110,000 years between peaks. So part of this is caught up in a resolution of TCN dating, and to correct for part of that is to run this in natural logarithmic space. On the top, you can still see the linear age space 10 to 2, 10 to 3 with the tick marks where appropriate. And our peak ages here are still in linear age space. This is 106,000 years, 120,000 years effectively. So that still gives you a good idea of where they actually land. But for this data set, for very old data set, I would say that this is probably the most reasonable plot. And we're being consistent with our previous interpretations, because if we look at bandwidth, I'm sure I haven't looked at this yet, but let's do it now. This is going to give us our smallest bandwidth, right? So 0.0726 for MAD. Let's run STD. 0.17, right? So that's an order of magnitude bigger. And for mean, 0.16, also about an order of magnitude bigger bandwidth. So this is definitely the way to go. Let's recalculate that one more time. For the publication plot, instead of putting in a number in this box, we're going to put in a capital R, and that will generate our kind of regional plot for us. The component Gaussians are outlined in red. Those are, again, external uncertainties. There are no internal uncertainties to plot for a data set like this. You can see a little bit of mismatch right here, like maybe these two really should be separate, but the uncertainties are so wide, it doesn't really matter that much. All we know is that something happened out here. So having a very broad glacial event is probably the best that we can say. I wouldn't call this a glacial event, this a separate, climatically important deglaciation event. We just know something's going on out here, but that's pretty thin evidence there. You can see the number of ages in the plots here. There's no necessary requirement of 3 ages for an event. We have 2 ages in Gaussian 4, which is 248,000 years ago. Would I hang my hat on this as being a independent glacial stage? No, not necessarily. Maybe for one of these other ones that have a lot more ages in them. Again, the evidence is pretty thin, but at least the uncertainties are much tighter than this other one, right? So 370 plus or minus 50, that's quite a spread. Effectively 250 plus or minus 20, that's a lot more reasonable. If you want to dig into these more, you can enter a component Gaussian and take a look at that plot and see, which 2 ages is this one grabbing, right? Or for Gaussian 3, for example, here. Actually, you see it on the original plot too. It highlights in the color of the Gaussian, so we have 2 there. We can grab Gaussian 3. You can see what ages Gaussian 3 grabs, right? It's this set here. And how they overlap with each other. And I'm quite sure there's going to be quite a bit of overlap with Gaussian 2. Because again, we're sharing probabilities across this because we built this composite probability density estimate. So you saw some that were pink get overwritten as cyan, right? But you can see that in these individual plots as well. This age in particular is shared by both. So you do have the ability to dig into this data and see which ages belong to which group. But in terms of presenting this data, I would stick with this regional plot that I generated by putting a capital R in here to show the different groupings. So 106,000, 107,000 plus or minus 9, 119 plus or minus 7. A bit of overlap there, but enough data, these 3 and these 3 to really kind of separate those two. Okay, let's move on to the next data set, which is old, not very old. We're going to keep it an external, and this data set runs between 30 and 100,000 years. It's kind of the dividing line between using linear age space versus a natural log age space. We're going to calculate our 3 bandwidth estimators again. We got a good model fit here, so no problems there. Got our square value, good p-value. Same thing for standard deviation. And for MAD, nice fit there in the model, nice R-square, nice p-value. So these ages, as you can see, run from about 95, 93, right? So not quite 100 to about just over 30,000 years. The 30,000 year to 10,000 year group was cut off and made into its own data set. Because there were so many ages, they would swamp the signal from the rest of the regional comparison. So we pulled that out just because there's so many data points there. So if we look at this, we had 3 good model fits, which is reasonable. The mean and the standard deviation, again, are basically identical, so that's great in terms of consistency. But they're both, I would say, definitely over smooth for looking at the convolving regional events, and I would go with the mean absolute deviation again, which is definitely going to have the smallest bandwidth compared to the other two. Which you can see here, we have a bandwidth of about 3, and the bandwidth for mean and standard deviation was about 7, so much bigger. So I would definitely stick with this narrow bandwidth to pull apart my different events. Some of these ages look very familiar from previous papers published, events at around 80,000, some at 45, some at 60. I've seen in several publications throughout the region. And there's our regional plot when we enter a capital R again. These are all external uncertainties again, and the number of ages underneath each one is listed at the bottom of the table that you can save. So let's look at this same data set in natural logarithm mode. Calculate MAD again. We've got a few squiggles here going on. Nothing too bad. Pretty reasonable fit. Good R-square value. But I wanted to show this one in particular because we have a problem here with Gaussian 4. This is a nested Gaussian. It's completely enclosed by Gaussian 2. It's just kind of separating out that little bit of peak there. I really don't like that, and I wouldn't recommend anybody pick one of these because I think this is basically overfit. You shouldn't have one Gaussian completely nested inside of another Gaussian. A good degree of overlap is okay. 50% overlap is fine, but being completely nested in like this, I really don't like that. So I just wanted to highlight that for everybody. I don't consider this valid as far as a fit goes. Let's look at the mean and the standard deviation, natural logarithm space. Get rid of these two. And let's look at their linear age counterparts again. Okay, so we have the 2 standard deviations, as we can see in the titles. Standard deviation, linear age and Ka, natural logarithm of age, and what we see is statistically indistinguishable fits. That's what I was saying. This is kind of the dividing line between whether or not you need to use the natural logarithm age space for your model fitting. Same here again, 63, 38, 37, 1,000 years difference, basically the same. Now, if we had run these ages from 100,000 all the way down to 10,000, maybe that would be enough of a spread to where we would get better fits using the natural logarithm age space, but since I cut it off at 30,000, it's just not necessary here. The spread of ages isn't big enough. Like the very old data set went from about 100,000 years all the way to 400,000 years. That's a really big range. So that's why that natural logarithmic space there with very old things is effective. Okay, we're going to move on to the global last glacial maximum. As I've said, named it. It's kind of broad for that, but that's fine. It's just a tutorial again. We're just kind of grouping things roughly together. So it's basically, 30,000 years down to Holocene, down to about 10,000 years. Good model fit in the mean bandwidth estimator. We've got a little bit of a weird loop-de-loop here. Don't love that. So some divergence on the standard deviation. You can see that here. It's kind of a mismatch between this secondary peak and the model, and then this tail end and the older stuff there. So let's just keep that in mind. I wouldn't recommend picking a model like this. And let's look like at the MAD, right? Decent model fit here, more symmetrically distributed than the standard deviation was. And so especially when you have other options, I don't see how you could justify going along with this mismatch. Statistically indistinguishable fits are given by the mean model without that mismatch, so that's definitely out. And both of these gave good model fit. We're missing a little bit in this older age, and this tail here. That's this little whoop-de-doo we see down here in the bottom of the model fit plot. That's not such a big deal in this case, I don't think. And we've got all of our probability peaks are kind of sticking out, independently. This isn't completely nested underneath Gaussian 4, so that's fine. This has a high degree overlap, but it's not being completely nested. It's totally fine. And again, going for the one when you have two good model fits with the narrowest bandwidth, especially looking at regional data where we want to separate out events, this is the way I would go. Produce our regional plot here. And we can see our groupings here, 12,000, 15.5, 18, 21, 26. And those seem like pretty reasonable ages for glacial events or deglaciation events in the Himalaya. So let's move on to our younger landforms, which are effectively Holocene, 10,000 down to 1,000 years, that order of magnitude range. We have our mean plot, good model fit here. Standard deviation, decent model fit. Got a little lump in there. Seems like that's just a little underestimation of the height of the probability peak here. Sorry, overestimation of the model compared to the probability density estimate, which is lower. And a little bit of mismatch down here on this old age edge of the curve, which is this kind of curving of the model here compared to the one-to-one line. So it's fine. Nothing too terribly wrong with it. This is a little bit better with a MAD, more evenly distributed. And again, thinking about which one gives us the narrowest bandwidth. So the residuals on this one was not as good because of those two model fit kind of discrepancies over here, and also the bandwidth is wider, so that's immediately kind of out of the running. So we're looking at the ages here. As you can see these, roughly, that makes sense. 4 clusters in here. Data visually, you can see that here again in the distributions when you look above the kind of like constant background noise of these long-tailed probabilities. Some of these ages with very wide uncertainties in the bottom there. And, the results are, again, statistically indistinguishable from each other. At this point, it's kind of a data quality question on which one you would go with. Definitely here, I'd go for the MAD bandwidth estimator again, basically because the bandwidth is smaller. When you're into younger data sets like this, the mean could give you a smaller bandwidth. It just depends on the independent ages. If some of these ages with very wide uncertainties were just a little bit smaller, then the mean may in fact give you a smaller bandwidth here, maybe slightly more narrow component Gaussians, and that would be better. But with the age data set that we have, MAD's giving the smallest bandwidth estimate, so 0.6896. Let's just confirm that. Yeah, 0.8149 for mean. So I would go with MAD, and that looks like a fairly reasonable distribution with a fair amount of overlap like you would expect. So we're not underestimating uncertainties here. Okay, and the last data set is the recent landforms. Still in external uncertainties, of course. This is that's a reasonable model fit. It's not perfect, but it's very symmetrical around our 1-to-1 line, right? So we're not skewing off to one side or the other, even though there's like some minor dispersion there. And that's, a pretty good data set. It's pretty impressive. It's effectively normal already with just one Gaussian. Let's calculate the standard deviation. Okay, got a nice model fit there, no problems. Got our square value, good p-value. And calculating the MAD bandwidth. Okay. So up until now, I've been talking about deconvolving as many component Gaussians as possible. That tactic kind of changes here for things that are very recent, 1 or 2,000 years. We really need to start considering what is the resolution of TCN dating. All right, so distinguishing 4 events within a 500-year age spread seems to be a bit dicey to me. So when we're looking at these young ages, I'm going to suggest as a rule of thumb to stick with the mean bandwidth estimator. And the reason why is because it uses the mean of the uncertainty of all the independent landform ages. And I think that's really important because that kind of prevents you from going too small, right? From dicing up things beyond the resolution of, sample measurement uncertainty and production rate uncertainties within the area. So I would stick with the mean with very young stuff. Now, if we had more samples, if we had 30 samples in here and the mean was actually, able to split out 2 or even 4 events from a 1,000-year period, if we had enough data to justify that, I would totally stand behind it. But I'm not really comfortable and wouldn't recommend going for uncertainties this small. If you were to go for something like MAD at this young of age range, you're effectively saying that you can tell the difference of, this is 46 years is the uncertainty on these, 36 years on this one, 32 years on that one. That's way too far. And so I would ignore that. Same reason for this. I would stick with the mean to keep yourself out of trouble with very young age data sets. And the fact that this comes back basically normal is actually really interesting. It just tells us that recently some things have deglaciated, and in all reality, some of these landforms may or may not be ice cores. Some of them, honestly probably haven't reached early stabilization yet, since these are glacial moraines. Maybe they are going to degrade a little bit before they settle. So I think that this is a reasonable estimate. And let's just calculate that one more time and look at what the uncertainty is. So the age is, give us our R here, 480 years plus or minus 200 years, so effectively 50% uncertainty, but that's kind of what the spread of the data is, and I feel like that's an honest assessment of something so young. Okay, that kind of concludes the regional analysis using PCAT. Again, if you have questions on how to use PCAT or questions about your data set or how to interpret something, please feel free to contact me. I'm happy to offer advice, and thank you very much for watching this.